Okay, in this class, we're going to be looking at rules of naming complexes. Now, there are various rules of naming complexes. Now, I'm going to take you through some of the rules for naming complexes. There are still some other rules, but these are like the major rules you have to observe in order for you to name a very good complex. Now, let's go with the first rule. If a metal is present, a non-transitional metal, that is a metal which is not part of transition the transitional part of the table, if I put it that way. Okay, that's like a good self-explanatory way. Then the metal is named first. Examples of these metals include sodium, potassium, magnesium, calcium. Just keep going like that. Strontium, just like that. Now, the second rule, ligands are named immediately after the metals. All these rules are important when you're naming your complexes, because if you miss a rule, you might end up making a big mistake and actually missing the name of your complex. Now, the second rule, like I said, ligands are named immediately after the metals. The ligands are named in alphabetical orders. If an anion, if it's an anion, if the ligand is an anion, the name should end with O. This is very important, very, very important. This O part. The name of the ligand should end with O. If it's an anion and you just use the normal name to end it, you end up failing everything completely. The name should end with O. Please take that. Example: chlorine will turn to chloro. Bromine turns to bromo. Thiosulfate turns to thiosulfato. Cyanide turns to cyano. Ethylene di ethylene diamine tetraacetic acid turns to ethylene diamine tetraaceto. Now, don't mind this, I just included it later. If a non-metal is present, the name should go last. Examples of these non-metals include chlorine, bromine, and sulfates. This is sulfate ion. They are all non-metals, regardless of them being in their compound form or in their elemental form. They are all non-metals, and this is an important rule. It's not part of the ligand. These non-metals here, they are not part of the ligand. They are on their own. The ligand complex is combining with them. Like the one in every like a ligand in every ligand, you always see a square bracket. Whatever is in the square bracket is part of the complex. Why this is what this entire complex is attached to. Do you get it? Okay, let me go further. The name of neutral ligands should remain the same. Examples of neutral ligands include water, but in this topic, we're going to be calling water aqua. If you're naming water, don't say water, don't say H2O, call it aqua. This actually like the came this actually where the name water was actually derived from. So it's still the same thing. Now, ammonia, we don't call it ammonia, we call it amine. We call it amine, not ammonia. Now this is ethylene diamine. Look at it. This is the complex, or what? Yeah, it's a complex. For short, most of the time you see them using En. En is like the short form of ethylene diamine. Nobody has the time to be writing the name of this complex. It's so stressful to be writing it every single time you want to ask a question on it, or whenever you're trying to process it. So they just gave it the name En. Its name remains the same, ethylene diamine. That's like following this rule. Do not change the name of the complex at all. That's like obeying the rule. Now let's go further. Transition metals have different names in their cationic and their anionic form. Now take this into consideration. Let me just explain this a little bit. I'm going to be writing downward. When a metal is present, let me just use Na, and the square bracket represent the transition metal. When a metal is present, the metal then becomes the anion. Anion are positively charged element, and then the transition metal becomes the cation because like opposite attract. So the anion actually attract the cation, or the cation attracts the anion because the cation is meant to have a lone pair of electron, and the anion is always electron deficient, so it ends up being attracted to the cation. In the ionic form, this will tend to have a plus and this tends to have a minus. Now, in the anionic form, they tend to be the anion here, the ones with the positive charge. Now, cations, like negatively charged elements, example chlorine, chlorine will therefore be the cation with a negative charge. Now, you need to take all this into consideration. In their cationic form, they have a different name. In their anionic form, they have a different name. Don't worry, it's looking kind of complex, but when you keep practicing, you find out that all these rules actually just blend and goes to your head immediately. You won't even really be considering, am I obeying this rule? Just like organic chemistry naming, at first it was complex. Now it's not complex at all. We get used to it and we keep going like that. Now these are the first 10 transition elements, and these are the names. I'm going to be giving you the names in the cationic and the anionic form. Now for scandium, in its cationic form, the name is scandate. In its anionic form, the name remains the same. Note something about the anionic forms. In the anionic forms, their name does not change at all. That's the fun part about it. So you don't need to be learning two names. In the anionic form, their names remain the same, but in their cationic form, their name changes. So for now, I won't be talking on the anionic form. I'll only be emphasizing on the cationic form. Now for scandium, the cationic name is scandate. For titanium, the cationic name titanate. For vanadium, the cationic name vanadate. For chromium, the cationic name chromate. For manganesium, cationic name manganate. For iron, the cationic name ferrite. For cobalt, the cationic name cobaltate. For nickel, the cationic name nickelate. For copper, the cationic name cuprate. And for zinc, the cationic name zincate. Now you need to know like something common in this. You all know like the symbol of iron and copper. Whenever you're writing the symbol, you don't write IR for iron. That would be rubbish, and that would be a rubbish symbol even to be thinking of it. Instead, for the symbol of iron, we write Fe. Fe is coming from the name ferrite or ferro something. I don't really know the name. All I know is ferro, and that's like the Greek name or wherever the names are derived from. Same thing for copper, we write Cu coming from cuprate or something relating to that. Now to go further, this I will give an example. We all know transition elements. There is a common property, like when you're given the unique properties of transition elements, is that they have various of what should I say different oxidation states. Like if I give an example, manganese has either 4 to 5 oxidation states. It has the +2 oxidation states. It has the +3 oxidation states, if I'm not mistaken. It has the +4 oxidation states. Okay, I think it doesn't have the +3 oxidation state. It has a +2, +4, +5, +6, +7. Just manganese alone. So all transition metals except from zinc. Zinc is not actually a transition metal because it does not obey the rule for transition metals. Transition metals are meant to have lone pairs, or what should I say, unpaired electrons in their d orbital, but zinc doesn't. So zinc is a d block element, but it's not a transition metal. Take that into consideration. I'm sure you've heard of it before. Now, for something like scandium, scandium only has one oxidation state, but you have to note this. That's scandium too. But note this: you always have to calculate your oxidation state, because if you don't calculate your oxidation state, you might end up giving a wrong oxidation state, and once you give a wrong oxidation state, you end up missing it. Now the rule is the oxidation number of the transition metal. This is meant to be IS. Sorry for the mistake. Let me just try and shade this. The oxidation number of transition metals is then put in brackets at the end. Whenever you're done naming a transition metal, you put like the oxidation number in brackets. Now, if I want to give an example, I've given an example on manganese. Now, for something like iron, the oxidation number we can expect +2 and +3. That's it. So if it's +2 and we are done naming the complex, then we put the oxidation number. If it's 2, we write 2 in Roman numerals at the back. If it's 3, we write 3 in Roman numerals. Always write it in Roman numerals like you're writing, just like naming normally. But always remember the oxidation numbers. Now, those are like the end of the rules, like the common rules I need to take in that I need to take in consideration. I just want to add one more rule to this. Just take this out. Let me just add one more rule to this. Now we've all heard of that there are different types of ligands depending on the number of lone pairs. For a monodentate ligand, that means he has one lone pair. For a bidentate, it has two lone pair. For tridentate tree, but they normally classify from tridentate, tetra, and they normally call them polydentates. Now take this into consideration. Let me call this rule 9. Regardless, just leave monodentate ligands out of this. Once you have a bidentate ligand, bidentate or polydentate ligand, okay. Once you have a bidentate or polydentate ligand, okay. I'm sorry, I need to clarify something. Sorry. Okay, we're back. Once you have a bidentate or polydentate ligand, the first thing you need to do is if they okay, my rule the rule I was actually going to emphasize, let me just talk on it now. Now, example AN, this is a bidentate ligand. I told you this ethylene diamine, EN, and they give you like 2 moles of EN. That's it. Let me just put it down here, like EN, like this. You don't name it diethylene diamine. You end up failing it. Instead, this name di is changed to bis. BIS. Same thing for tree. EN. Tree is changed to trace. Now let me just like use, if you've understood what I did here, I'm sure you've understood. Like, instead of it to be by, the name changed to bis. Instead of it to be try, the name changed to trace. Now I want to give a table on all of this so you can take into consideration. Now, okay, let's say this is like the number of ligands present, and this is the name. Note, this rule only applies for bidentates and polydentate ligand. Okay, now for 2, instead of it to be bi, the name changes to bis. For 3, instead of tri, the name changes to trace. For 4, instead of tetra, it changes to tetrakis. For 5, pentakis, and so on and so forth. If I put it that way, 6 hexakis, 7 heptakis, 8 octakis, like that. Just now for 1 and 2, you can know that it's just to add S. for 3 down to infinity is to add KIS. That's just the rule. Nobody will give you more than that or less than that if I put it that way, but they can test you with that. Now we have an example here. Our first example, we are asked to name this ligand. So from our rule 1 actually, I can still remember, I told you that the name of, when there's a metal attached to the complex, the name of the metal comes first. So we have, first of all, potassium. This name is constant, potassium. Now after that, the next rule I said, the name of the ligand comes next. And if it's an anionic, if it's a cationic ligand such as CN, the name, instead of it to end with the normal whatever it's ending with, it ends with O. So therefore, this cyanide will end with O. And since there are 6 molecules of cyanide, it's called hexa. Just like your penta, hexa, tetra, and all the stuff. So it is hexacyano, and the name of the ligand comes next after the name of the metal. So we have potassium. You need to give a little space here. Always give your space. Always give your space. Do not try to minimize space. That's like what some people be actually looking at. They always want you to give your space. Potassium hexacyano. Now after this, I gave you a table. In that my table, in the table, look at the table here. I said for cationic form of transition metals, the name, it's always going to be changed. And in this form now, this, if we're dividing it into their basic ions, we find out that the complex is a cation and the metal is an anion. So we have to give ion the cationic name. So that is the next thing. Potassium hexacyano ferrate. 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 Not ion. We call it ferrate. Potassium hexacyano ferrate. Now the next thing I said in my rule, you always have to end the name with the oxidation state of the transition metal. Now we have to calculate the oxidation state of the transition metal. Now we know potassium. Potassium has an oxidation state of what? +1. And cyanide has an oxidation state of what? -1. So it's so easy. There are 4 moles of potassium here and there are 6 moles of cyanide ion here. Now it's so easy to calculate. I'm sure you guys know how to calculate the oxidation state. So I can now say, to add this total, I can say 4 molecules of potassium, that's 4 times -1. And that of cyanide plus, since we're looking for ion, we can include it as Fe, plus that of cyanide, that is 6 moles -1. Now we can say it's -1 is equal to 0. Now I'll have to write this name above so I can have space to calculate. Or to do my calculation. So let me clean this. Let me just write the name above. Potassium. Potassium hexacyano ferrate. Now we want to calculate the oxidation state, so I can erase this. Please don't get confused. Please don't get confused. I'm actually going to leave this here. Let me leave this in a bracket so it doesn't like confuse you. We've already done this. Now I'm going to the top to continue my calculation. Let me put it in a bracket again, or in a box. Now we have 4 plus Fe minus 6 is equal to 0. So this goes here. This also comes and joins the party. And we have Fe is going to be equal to 6 minus 4. And then the oxidation number of ion then turns to +2. I told you have to write the oxidation number in Roman numerals. So we have ion 2. Potassium hexacyanoferrate ion. Potassium hexacyanoferrate. So you see how the name can confuse you. Potassium hexacyanoferrate. So, but when you get used to it, once you've solved a lot of questions, you will find out that at the end of the day, once you're saying the wrong thing, it's actually like bugs you. You feel like, am I correct? Let me just check it again. The rules go on and play in your head again, and you're able to like solve it again and get your answer. And once you get your answer, you don't debate it because you already know the rule. So your answer is your answer. You just smile, pick whatever they give you, and go on with it. Now I'll give you time to just pause the video since I don't want to waste more time. So you can pause the video and solve this. But meanwhile, let me give the correction. Now, I told you the first rule. It's still the same rule applying because we have to calculate the oxidation number. I'm going to actually be leaving some gap downward. So we have the name sodium first, like before. Sodium. Then there are four moles of the ligand. So we have tetrachloro. Chloro. I told you not chlorine. Tetrachloro. 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 Now, the nickel is in its cationic or anionic form. You can pause the video and give the answer. But the answer to that question is it's in its cationic form. And I told you, like the former example, in their cationic form, their name ends with 8. Their name changes from the normal name and ends with 8. So we have nickelates. Nickelates. Now we have one more task to do, and that's to calculate the oxidation number. Now we know sodium, so like potassium has +1, and chlorine, like cyanide, also have -1. Now to calculate the oxidation number, like before, we have 2 in brackets +1 plus nickel plus 4 in brackets -1. Then we can actually take this is equal to 0. Always complete your equation. Then take this 2 to this side. Then we have 4 minus 2 is equal to nickel. Therefore, nickel is equal to 2. We've calculated +2. So we calculated our oxidation number of nickel. Now we just have to write it in Roman numerals here. So our final answer is going to be sodium tetrachloronickelate 2. Now I have one more example. This example talks about the rule, the last rule I gave you. Okay, the last rule I gave you, that's what this example is actually talking on. I've removed the rule, but I hope you got that rule. If you didn't get it, you can go back to the video and actually check on that rule because that rule is so important. Now in that rule, I told you for a bidentate or a polydentate ligand that has 2 or more molecules present, we don't give the name bi or tri again. We change it to trace, bis, tetrakis, pentakis, hexakis, octakis, and so on. So now this right here, it's EM for short. That's ethylene diamine. Now if we look closely, we find out that sorry, if you can see this arrow, good for you. We find out that there are 3 molecules of it present. So are we still going to give, is the name still going to be ethylene, triethylene diamine, or is it going to be triethylene diamine? You can pause and give an answer to your question, or you can just go on with me. We're actually going to figure that out. Now look at this also. In this form now, I love this question, it's different from the others. In this form, the complex that we have here now, it's in its anionic form. because we all know that this is sulfate ion and it's in its cationic form. It's always in its cationic form, is a cation, while this is anionic form. So in our naming, we have to be careful. We have to be careful. It's not like the former one that will go for cobaltate. Now we are not going for cobaltate at all. So let's continue. I said the name of the ligand goes first when there's no metal present. So let's continue. Now the ligand, like I said before, the name is going to be trace. That's the answer to that question. Not going to be try. So now we have trace ethylene diamine. Okay, we have trace ethylene diamine. The cobalt, it will not be cobalt. It's not be cobaltate. Instead, it's going to be cobalt because it's in its anionic form. Ethylene diamine, cobalt. Just as before, we need to find the oxidation state. After the oxidation state of the cobalt is found, then the name of the non-metal comes last. That's like the final name. Whatever is present, that's like the final name. So we have cobalt. Now we need to calculate the oxidation number of cobalt. I could have written this on the top. So let's start again. Trace ethylene diamine cobalt. Now we need to calculate the oxidation number of the cobalt. Now En, I want to write this for short. I can't be writing this. I told you it's going to be really complex. En has an oxidation state of 0. I told you in my former rule, ethylene diamine is neutral, so it has an oxidation state of 0. Sulfate has an oxidation state of what? You can answer a question. Sulfate has an oxidation state of what? +2. I mean -2. So we have SO4 -2. Easy. So now we have En. Now note, it's 2 molecules of the complex that are present in this, not 1 molecule. It's 2 molecules. So we have to take that also into consideration. So we have 2 in brackets 0, that of En, plus 2 of cobalt, plus 3 of sulfate is equal to 0. Now if we do our math, we find out that this ends up going out. So we have 2 cobalt is equal to, I'm taking this to the other side, so from the negative sign it turns to a positive sign, 6 plus, divide all by 2, then we find out that cobalt is in its +3 oxidation state. Now if you look at this, now if you look at this, cobalt could also be in its +2 oxidation state, like I said before. So if you're used, most of the time cobalt it's in its +2 oxidation state, but now it's in its +3 oxidation state. +2 is mostly stable, that's what I'm actually trying to say, but now it's in its +3 oxidation state. So you're going to think, if you didn't do this calculation, this easy calculation, if you didn't spend like a minute or two doing this calculation, you would have written cobalt 2 mistakenly, and cobalt is in its +3 oxidation state. At the end, you end up failing the entire question. So the oxidation state of cobalt here is 3. So I'm going to actually be writing this sulfate downward. So we have sulfate. That's it. That's it. Now the name, like I said before, is tris ethylene. That's an N. Tris ethylene diamine cobalt 3 sulfates, and that's the name of the complex. Now if you didn't actually go through all these steps, or learn about the rules. You can look at this and just be ignorant of the question and say, what type of question is this? But once you practice a lot more and you just practice a lot more, get a lot of questions for yourself, learn the rules. You don't even need to like actually cram them or do anything. Actually, once you be, if you don't practice, say practice make perfect. If you don't practice by failing like 2 or 3 questions, then you look where you went wrong. Then that actually sticks to your head. You become cautious of that mistake, and you end up not making that same mistake twice. Even if you've forgotten about that, maybe you're about to write an exam and you end up just about to make that mistake, that's your first previous error is actually going to like come back to your head and end up being so sensitive about that. That's I'm not encouraging you to fail, but that's like the advantage of trying not giving up. Because if you give up like immediately after one trial and say you can't get this, or you've gotten it, you're good at it without going further to practice and practice and practice, you don't know what can happen in exams. Sometimes failure makes us increase our sensitivity to like a particular case. And now if you actually feel this question when no one is actually recorded or actually grading you, you fail it, you feel some questions, you get some questions, you get good at it, it's going to be better, much better for you than when you get to an exam hall and you actually fail it there, because then it's going to affect your grade. That can affect your mindset. If this one affects your mindset, it's just for a short period of time, but that can affect your mindset for a long period of time. Thank you for watching this video. Like and subscribe to my channel. Thank you.